The following section that we talk about in Foundations 20 is talking about proofs that are not valid. Now, an invalid proof is proof that contains some kind of error in the reasoning or contains some kind of invalid assumptions. So basically things that are not true. A premise is a statement that is assumed to be true. Now, it may not be all the time, and that's where a lot of proofs do get to be incorrect. One specific type of reasoning that really produces invalid proofs is by using what's known as circular reasoning. And it's an argument that's incorrect because it makes use of the conclusion to be proved. And we'll actually see a case of that in one of our examples. So our first example here is we're going to talk about what type of error occurs in this deduction. So just like in section 4, we talk about deductive reasoning, we're using facts, all of that aspect. All people over 65 are retired. Leroy is over 65, so he's retired. Hopefully, all of you realize that not all people that are over 65 are retired. So this is using some language error. This is a premise that's incorrect. Oh, fix that a little bit. The word all can be a very sticky word in the math language. Now, when we're using proper deductive reasoning with our variables, with our x's, our y's, our n's, whatever it is, that makes things a lot easier. But using language within math, we tend to have a lot of difficulties with proving things being true, especially when you try and use an overgeneralization. So, not all people are retired that are over 65. Another one that's going to produce an error. And this one is actually the example of this is not circular reasoning. This is we'll see what the error actually is. So Beth claims that she can prove that 4 equals 3. And here's her proof. So we can see automatically here that this is a deductive reasoning proof. And the way that we know that's deductive reasoning is because we are just using letters. We could change these to x, y's, and z's. But suppose a plus b equals c. So just some number plus a number, another number equals c. So by expanding it out, the letter a, or more specifically 1a, can be achieved by taking 4 a's and subtracting 3 a's. That's still true. 1b can be achieved by taking 4 b's and subtracting 3 b's. 1c can be achieved by taking 4 c's and subtracting 3 c's. So far here, we're all still good. Now what happened in our next step is we did that Bev would have done a rearrangement. You'll see how she moved all of our letters that had the 4, our coefficient of 4 in front, and we moved them all to the left, and anything that had a 3, they got all moved to the right. Now, how did that happen? Well, if we have that's why I have a little bit of space here, 4a plus 3a plus 4b minus 3b equaling 4c minus 3c. So to move our 3a over, this is subtract 3a, so we'd have to add 3a. What you do to the left-hand side, we have to do it to the right-hand side. To move our negative 3b over, we have to add 3b. And then we add 3b. In the same breath, actually, I'm going to change to blue. We have our 4s, our 4a, our 4b. We want to move our 4c over. So we'd have, this is a positive 4c, we'd have to subtract a 4c. And from there, what we see is that our 3a's would be gone, our 3b's would be gone, our 4c's would be gone. So on the left-hand side, we'd only have a 4a plus 4b subtract 4c. On the right-hand side, we have a 3a plus a 3b subtract a 3c. So far, this would still be correct. Now, in order to get our next step, it looks like that Bev factored a greatest common factor. From the left-hand side, she factored a 4 out, and from the right-hand side, she factored a 3 out. Then to get to our next step, this is part that, actually, no, I'm not going to do that. I'm going to rewrite this just so we can see it. What happened, and again, this is why I have a space, so I can actually show this calculation, is on both the left-hand side and right-hand side, we see that both of them have this a plus b minus c. A plus b minus c. So she just divided them off. And when you take an a plus b minus c and divide by an a plus b minus c, they would be cancel off. A plus b minus c, they cancel off, and therefore 4 equals 3. So what's the error? The error comes in this last step before we get to this 4 equals 3. Because it's using the fact that a plus b, so with us starting with a plus b equals c, that part's fine. But you see in this step, we have an a plus b minus c. Well, what happens when you subtract c from both sides here? You have an a plus b subtract c equaling 0. So in this step, she did divide, but she divided by 0. And you cannot do that. You can't divide by 0. In the pre-calculus side, we'll talk about what that relates to graphically. Talk about in the pre-calc 20, we talk about non-permissible values, as well as we'll talk about something else in a later unit. Pre-calc 30, we see all of it graphically as well as algebraically, but you just can't divide by 0. So that is the error. Divide by 0. Can't do it. Now, Liz claims she proved that -5 equals 5. So if we assume that -5 equals 5, you square both sides, and you properly square -5 by putting in brackets and squaring 25 equals 25. This is that case of using the conclusion to try and prove our answer. So this is that circular reasoning. That's that third definition on our page. Argument is incorrect as it makes use of the conclusion to be proved. So starting off that -5 equals 5, well, no, it doesn't. This is -5. and that's positive 5. They're not the same. Right, a number trick proof. Jose is trying to prove the following number trick. Choose any number, add 3, double it, add 4, divide by 3, take away the number you started with, and each time Jose tries the trick, he comes up with 5. His proof, however, does not give the same. What is the error in Jose's proof? So Jose's proof is here. Choose any number, x. I know the textbook will sometimes use the letter n. X is good, n for a number, it's all good. So his next step was add 3. So let's make sure that he added 3 correctly. X add 3. Or it could be n plus 3. Okay, so far good. So far so good. His next step is double it. So when you double it, by multiplying 2 times by an x plus 3, you distribute the 2 on the x, you distribute the 2 on the 3, 2x plus 6. Awesome. So if we did the same thing with this 2 multiplied by an n plus 3, it'd be a 2n plus 6. So far so good. Add 4. Now if you just add 4 to here, what some students will actually do incorrectly is they'll say add 4 and so don't write this, and then they become like 6x. So, oh, sorry, I'm actually in the wrong spot. If you add 4 to this, some people will incorrectly do it this way, and this is one error that happens with proofs. 6x plus 6, but the number 4 does not have an x. It's just the number 4. So where are we adding 4? We're adding 4 onto the number that doesn't have a variable. 6 plus 4 is 10. So far so good. Then we divide by 2. So taking this, so to divide by 2, well, what we're doing is we have to make sure we divide the 2x by 2 and the 10 by 2. And that's where Jose's error is. He divided the 10 by 2 to give us 5, but 2x divided by 2 is not 2x. It's 1x. If using the n's, this step would be a 2n plus 10, but dividing by 2 would be an n plus 5. And the last step for the proof, take away the number you started with. Well, the number we started with was an x or an n. So if you take away x from here, and subtract x, you're left with 5. You take away n, you're left with 5. So this, or if you use the x's, x, add 3, double it, add 4, divided by 2, take away the number you start with. This are the deductive proof to Jose's number trick. So, what is the error in Jose's proof? You didn't properly divide by 2. You only divide the 10 by 2. You have to make sure you divide everything by 2. Now here is one probably the most famous invalid proofs. Now some people will use puppies, some people will use girls, some people will say kittens. You can use boys if you really want to. You could say, we won't do that one. Anything that's are not evil, here is the proof that anything you really want to is evil. So we know that puppies require time and money. Well, as the phrase goes, we also know that time is money. So we could rewrite that first question, or that first line, to say that since time is money, we could write money instead. So money times money. Oh, well, this can be simplified. Money times money would be money squared. Now, what we also know is that money is the root of all evil. So money is the root of evil. So instead of writing money in this step here, puppies. So instead of writing money, we could write, so since money is the root of all evil, it is root of evil and squared. Well, what happens when you have a square root and a square? They cancel off. So therefore, puppies are evil. Girls are evil, kids are evil, boys are evil, whatever you want. Now, why is this an invalid proof? Hopefully, if you're thinking about it, you know that puppies don't just take time and money. They take a lot of extra things. Time is not the same as money. The phrase of money being the root of all evil is also not correct. So it's using it's using a whole bunch of invalid assumptions with the language to come up with an invalid proof. So that is sometimes the fault behind trying to combine math and language. But there's going to be many times that we do combine math and language. And we have to be just very careful. For example, using the word all. Being careful with what we're doing with the language as it connects to math. And using really bad assumptions. All right. You can go have some fun.